through these guidelines in there, but basically the guidelines say think about the problem, think about different patterns that this might fit into, right? A lot of times use substitution might work. You might need to trick it or to manipulate it in some way. And the better manipulator you are, the more you understand mathematics, the better manipulator you are. Just like if you want to manipulate a person to do something that you want them to do that they don't necessarily want to do, you really have to understand them and know them in order to do that. And it's very similar with math, except this isn't wrong, right? Manipulating people is wrong, but manipulating math is not. So you really have to understand the rules, the functions, and how all of this beautifully fits together for one common goal. And that's just to be amazing, because that's what math is. Looking here, we have a differential equation, and we want to use substitution and the log rule. So see what you can do with this. And remember, when we solve differential equations, that just means that we are integrating. Okay, so you are integrating dy over dx, and that's where you would end up getting y, and you're integrating the 1 over x, the natural log of x. So see what you can do with this, figure out what your u would be, and then solve. In this case, your u is going to be the natural log of x. When you find the derivative, you get 1 over x. And when you solve for dx, you get x times du. And we are going to take that and substitute it in. So this should be that we can bring this dx over if you wanted to, or you can remind or keep it over there as well, whichever way you wanted to do that. But then when we integrate, you would then get y equals, oops, we didn't integrate yet, but when we integrate, you get the 1 over x times u times x times du. Kind of running into my other stuff there, but you can see that these x's will cancel, that x and that x will cancel, and so you really just have the integral of 1 over u du. And we can integrate that. We know that that is going to be the natural log. Right, and then when you plug in your u, which is the natural log of x, you get y is equal to the natural log of the absolute value of the natural log of the absolute value of x plus c. And that would be your solution to that differential equation. So instead of doing this problem that was in our notes, I'm going to switch this to tangent of x. All right, so we're integrating tangent of x dx. Try this one on your own. You have to get tricky. You have to rewrite tangent as something else and then use u substitution. See if you can try this one on your own and come back to the video if you need any hints and pause it. The more you try and do on your own, the better off you'll be. If we switch our tangent to sine over cosine, and use u as cosine, we're going to end up dividing by the derivative of that, which is negative sine. And when we do that, that's where your signs will cancel. You'll still have this negative, right? We still have that negative up front, but now it's negative the integral of 1 over u, and that's just negative natural log of the absolute value of cosine of x plus c. Okay, so it took a little bit of trickery there, but we were able to figure out how to rewrite tangents so that we can actually integrate it. Here's some rules. You don't have to memorize that because, you don't have to memorize these because we just did this one. Right here, the integral of tangent, we just did an example of that one, and it's negative natural log cosine of u. But I have all of the other ones here if you want to have them down. It might save some time if you come across them, like if you have the integral of, if there was like a 2 out in front here, right? 2 cotangent, then it's just going to be 2 natural log of the absolute value of the sine. So they could save some time, have them down, have them in your notes. I wouldn't say memorize them, but have them available and know when, where, and how to use them. Let's do an example using one of these. Here we have the integral of the square root of 1 plus tangent squared. And if you remember, 1 plus tangent squared, right here, you're going to use the fact that this is equal to secant squared, because now, instead of having u as 1 plus tangent squared, then we can look at just integrating the secant squared. And when you end up putting secant squared in there, the square root of the square cancels out, and so it's just secant. Right? And that is one of our rules that we had up here. So go ahead and use that rule and finish this problem. This is a definite integral. You have an upper limit and a lower limit. Okay. So when we integrate, you get the natural log of secant x plus tangent x, and then you have your limits from 0 to pi over 4. Then we plug in our upper limit. So when you plug in the pi over 4, you get secant of pi over 4, which is radical 2, plus the tangent of pi over 4, which is 1, minus the secant of 0, which is just 1. And this is all natural log. Hold on, I need to put the natural log. This is the natural log in front of that one. And the secant of 0, which is 1. The tangent of 0 here, this is just 0. So 1 plus 0, that's where this 1 comes from. And this is pretty much as far as you can go. I guess the tangent of 1 is just 0. So we can forget about that. Or sorry, not the tangent, but the natural log of 1. That's equal to 0, and so our answer really is just natural log of the square root of 2 plus 1, and that is as far as we can go for this one. I just have one more example, pulling in the idea of the average value. In electromotive force, E of a particular electrical circuit is given by E is equal to 3 sine of 2t, where E is measured in volts and T in seconds. Find the average value of E as T ranges from 0 to 0.5. So remember, the average value is 1 over B minus A times the integral. So when we're looking for the average value, it's going to be 1 over 0.5 minus 0, which is 0.5. Times the integral from 0 to 1/2, or 0.5, and our circuit is given by the function of 3 sine of 2t dt. It's with respect to time. All right, so try this one, pause the video, try this one on your own, see how you do, and then come back. Okay, so when we integrate, we're using u substitution. U is your 2t right here. And then when you make that substitution, dt ends up being du over 2. So you end up, dividing by 2 on the outside, which essentially cancels with this 2 right there. And that's where you would just have the 3 out front. And then I went ahead and changed my limits as well. So instead of using 1/2 and 0 and plugging 2t back in, I figured out, okay, in terms of u, what is 1/2 going to be? So if my u was 2t, plug in 1/2. So my new upper limit is 1, and my new lower limit is 0. And then when I integrate sine, I get negative cosine, and that's why I have this negative out front. Then when you plug in your upper, lower, and lower limits, when you plug in your upper, you get negative 3 cosine of 1. Plug in your lower, you get positive 3, because it's upper minus lower, but when you multiply this back in, that's why it becomes a positive. And so then you get positive 3 cosine of 0. This is some value. I'm not 100% sure what that is, but the cosine of 0 is 1, so this can be all simplified down to 3. So you'd have negative 3 cosine of 1 plus then just 3. We can factor that 3 back out or just leave it like it is. It just depends. Some variation of that that's equivalent would be just fine. And that is the end of the notes for the natural log function and using that to help us integrate. I hope you had a great time with this set of notes, and I look forward to seeing you in class. Now, if I can get this video to turn off here. Uh-oh.